let us discuss the Fraunhofer diffraction and intensity distribution of a circular aperture, a pinhole. Now, assume a circular aperture AB of diameter small d. Light will pass through it and get diffracted. The diffracted beam can be observed on a screen placed in front of the aperture. Now, when the beam diffracts through the aperture, it can be focused on the screen using a lens. The rays traveling parallel to the optic axis will be diffracted to the center of the screen, assumed as point P. And this will be a point of maximum intensity. Now let us assume a beam of rays that are diffracted from the aperture. Now the rays that are diffracted from the aperture at an angle theta, they will be focused at another point on the screen, and let that be P1. The angle between P and P1 will be theta. The distance between the central bright spot P and P1 is defined as x, and P1 may be a point of minima or maxima depending upon the path difference between the rays reaching at P1. Now to find that, we draw a normal between these two rays. And drawing a normal as such, we'll define the path difference as small d sine theta, where the angle between the circular aperture and the normal will again be theta. Now, similar to P1, there will be a identical point P2 below P, and it is placed again at a distance x from P. Now, P1 and P2 is a point of minima if the path difference is an integral multiple of lambda. Okay. And P1, P2 becomes a point of maxima if the path difference is an odd integral multiple of half wavelength. Thus, P1 and P2 will lie on a circle of radius x. Following these conditions for maxima and minima, we will obtain a diffraction pattern on the screen. And it consists of a central bright disk called the airy disk, surrounded by alternate dark and bright concentric rings called airy rings. The intensity of the bright rings will decrease gradually outwards from the center. This shows the diffraction pattern obtained on the screen. Now here, the diffracting angle theta can be written as sine theta is equal to x divided by f, if f is the focal length of the lens, right? Since diffracting angle is very small, sine theta will be approximated to theta. So theta is equal to x by f. Now, from the condition for minima, the first secondary minima can be written as path difference equal to n lambda. That is, here path difference is equal to small d sine theta is equal to lambda, since n is equal to 1. Thus, sine theta, which is approximately equal to theta, is equated to lambda by d. So we have two expressions for theta, and equating them, we get x by f is equal to lambda by d. That is, x is equal to lambda f by d, where lambda is the wavelength of the source light, f is the focal length of the lens, and d is the diameter of the circular aperture. But in practice, actually the radius of the first dark ring is slightly larger. Hence, we give appropriate corrections, and the expression obtained is x is equal to 1.22 lambda f by d. And this is an important equation. From here, we can infer that as the aperture diameter increases, the radius of the airy disk will decrease. This graph shows the intensity distribution of the diffracted light from a circular aperture. Now the diameter of this airy disk is the diameter of the central disk. It is equal to 2x. Hence, diameter of airy disk is equal to 2.44 lambda f by d. And the angular spread of the beam is defined as sine theta. It is obtained as 1.22 lambda by d. This gives an important application in sound. To make use of loudspeakers that give more directional sound waves, we have speakers with large diameters. Since small d will be bigger, the angle of diffraction theta will be smaller, and hence sound waves can be made highly directional. Thus, loudspeakers with large diameters have greater degree of directionality. Now, this is the diffraction pattern observed on the screen, and let us define the intensity distribution of this diffracted pattern. The intensity distribution in the circular aperture Fraunhofer diffraction is mathematically given as I is equal to I naught into the square of 2j1 of nu by nu, where nu is the phase of the diffracted beam and j1 of nu is the Bessel's function of first order. j1 of nu is a mathematical function called Bessel's function of first order. Graphically, this function j1 of nu is represented by this curve. Here, the intensity term is the square of this term. Hence, the negative values in this graph will all become positive values, and thus the intensity distribution curve is obtained as such. Here we can see that the intensity of the central spot is very much larger than that of the secondary maximus, and the intensities of the secondary maximus is gradually decreasing as we move away from the center. Now here, this slide just represents the nature of the diffraction pattern when you take apertures of different shapes. Okay, so if we have a triangular aperture, the diffraction pattern observed will be as shown here. Now for a square aperture, the diffraction pattern is as shown here. For an aperture of the pentagon shape, the diffraction pattern observed is as shown here. And if the aperture is the shape of a hexagon, the diffraction pattern observed is as here. So we have different patterns as the nature or the shape of this aperture changes. All these beautiful patterns are observed in nature. We just need to identify them. That's all for today's session. Thank you.